All right, thanks you very much, George Group, for the introduction and also for the invitation to speak in your colloquium. This talk will be about pointwise convergence for spherical maximal, for spherical means, first of all, and then as a consequence, LP estimates for those, and some more recent developments about local LP improving bounds. That means locally the operator maps into a better space than in LP, so in LQ for Q greater than P. And we'll discuss sort of motivations where these come from. So I should acknowledge work with a lot of people, and maybe the story actually starts in the 90s. There were two papers with Steve Wenger, who's also here, Jim Wright, about spherical maximal functions with restricted dilation sets. And then a later paper about finer endpoint estimates with Terry Tao and Jim Wright. And recently, we have taken up this subject of LP improving for local variants of the maximal functions. And so there is joint work with Tess Anderson, Kevin Hughes, and Joris Roos. And we'll mainly talk about recent developments in a paper with Joris Roos last year. There are some 3 related papers listed here, which I presumably will not have time to say much about. There is a rather long one about sparse domination, which serves as a motivation for these considerations about LP improving. So that's joined with David Beltran and Joris Roos. There is a related paper where one tries to quantify almost everywhere convergence by means of the variational norms, and that's joint work with David Beltran, Richard Oberlin, Luz Roncal, and Betsy Stovall. And there's some recent work on the Heisenberg group, which is a joint work with Joris Roos and Rajula Srivastav. So there's one paper which is posted, and we are currently working on topics which are related to this talk, but on the Heisenberg group. Okay, so let me start sort of with a historical overview a little bit, because this is a colloquium. And so we'll go back to the 1970s, when Eli Stein considered the spherical means of a function in RD. So we pick a point X, draw the circle around it of radius T, and average the function over this circle or sphere in higher dimensions. And then we let the radius go to 0, and we ask about convergence to the function. The average should converge to the function. So this is sort of a singular variant of the classical Lebesgue differentiation theorem, where we have balls. When the balls shrink to a point, then the averages converge to a function. And so Stein considered this more singular version. Now, it is from fairly easy examples clear that one cannot expect the same result as for the classical averages, which converge almost everywhere for all f in LP as p is greater than 1, even for p equal to 1. So there's some restriction on the p, but at that time it was remarkable that there is any result for such singular maximal functions at all. In fact, I read in some math review about, it was not the one about Stein's paper, but a related paper, and they call this maximal function an exotic maximal function. Well, nowadays, this is sort of a very standard object in harmonic analysis. There's nothing exotic about it. But at that time, it was kind of unthinkable for many people to treat questions about pointwise convergence or maximal functions by means of the Fourier transform. And Stein did just that. So, and that was in conjunction with other papers, partially joined with Steve Wenger and others, where the Fourier transform plays a big role in order to establish theorems about pointwise convergence. So nowadays, many of these arguments we can just view through the Sobolev embedding theorem with respect to the dilation parameter. A suit is simply replaced by a Sobolev norm, an L2 Sobolev norm, say, or an LP Sobolev norm, and then phrased in the standard framework of harmonic analysis that use the Fourier transform objects like that. But at that time, this was a very novel idea. Now, Stein's proof uses L2 methods a lot, and these do not work in 2 dimensions. And so for a while, this pointwise convergence question was open in 2 dimensions until Bourgain proved a positive result for the circle using completely new methods, which were kind of revolutionary at the time. So this was in 1986. So the result, if we combine these 2 papers, that in dimensions d greater than or equal to 2, this pointwise convergence result holds for all p greater than d over d minus 1. I mean, it's very easy to see that there cannot be any result in 1 dimension. So when you see this, t over d minus 1 becomes infinity, there is no result. And it's also standard, in fact, necessary by a very important old theorem by Stein, that when one proves some quantifying result for a maximal operator. So instead of taking the limit as t goes to 0, we take the supremum over all t, and then we form this maximal function, and we try to prove a boundedness result for this maximal function. It's perhaps a priori interesting if you look at this operator, that for a function in LP, it's totally not obvious that this maximal function should be a measurable function at all. Right? We take the supremum over singular objects, and the supremum is over a countable set. If we did it over the rational numbers, we would be okay. And so what one usually proves in these arguments, one proves a little bit more, namely one proves that for almost every x, the function of the average as a function of the radius t is continuous in t. So for almost everywhere x, it's continuous. And so then, of course, we can replace the soup of the real numbers by the soup of the rational numbers, and we have no problem with the measurability. Okay, so the topic here is what happens if we restrict the dilation set. So we do not take all radii, we just take some radii. And so we call this restricted approach sets. So we take a bunch of radii. I usually do not call them Rn for radius, but Tn for time, because of the connection with the wave equation. The spherical means come up in the wave equation, and so in other problems like that. So if those times or radii go to 0, say in a sequence or in a particular set which has accumulation point 0, and then we have the natural question whether we have pointwise convergence when t approaches 0 within this approach set. And so perhaps the first paper in that subject was one by Calixto Calderon, who considered the question of what happens when t goes to 0 in a lacunary sequence, say 1/2 to the k. And there's a related note by Kaufmann and Weiss, and both groups proved that you have a better result than Stein's result, namely you have almost everywhere convergence for f in LP for all p greater than 1. It's actually an open problem. I just mentioned this, whether this holds for p equal to 1. We come very close to it, but at this point, this is still an open problem, whether we have almost everywhere convergence for all integrable functions. But so we're not talking about that open problem. We're talking about intermediate cases. So what's intermediate between lacunary and all dilations? A very dense sequence of dilations converging to 0. Okay, so we can, for example, ask, what if Tn goes to 0, the set of dilations, as Tn is 1 over n to the alpha for some alpha, 1 over n, say, or sparser than that, but more crowded than lacunary, 2 to the minus square root of n instead of 2 to the minus n. Or a completely different question, what happens if T approaches 0 within the Cantor set? So for any of these examples, do we get a better result? That's the question. That was the question that we considered in the 90s. And phrasing this question like that, there is a very disappointing answer. And the disappointing answer is that it makes absolutely no difference for the 3 examples that I've written down. They're all as bad as the Stein maximal function or Bourgain result, namely convergence, almost every convergence only holds for p greater than d over d minus 1, the same range as for the full maximal function. Okay, so one shouldn't give up here, right? And there ought to be some intermediate results, and that's what we ask ourselves at that time. And analyzing these examples, one realizes that there's a particular feature of the spherical maximal function that we ignore, namely the dilation invariance. So if we conjugate an operator with dilations, that will still be on LP, but it will look very different. All right, and somehow a result should take this into account. And so, so this leads to the insight that one shouldn't look at this full set. One should look at what happens if we approach the origin, t equal to 0, in sort of dyadic intervals, 2 to the minus k, 2 to the minus k plus 1. And then we look what happens in every one of these dyadic intervals. So we get a bunch of t's. And then we take that dyadic integral and we rescale it back to the interval 1, 2. And then we look at what happens there. And so it should be that type of, it should be conditioned on that rescaled version that, that governs this problem. All right, so, so I would give you some intermediate model examples where indeed you get an intermediate result. So we take the dilations 1 plus n to the minus alpha, and then we multiply them by any dyadic number 2 to the minus k. Right? And so we form a set, and then we say what happens if within that set we go to 0, and then we get a true intermediate result. Now I should say that and the analysis of these model cases leads to up to endpoints to a very complete theorem about essentially the characterization up to endpoints of the range of these maximal functions. Now, I do not want to state these conditions. For the purpose of this talk, I would like to just stick with a particular set of approach sets which have this dilation invariance. Namely, I will start with a set E in the interval 1, 2, and then I'm going to scale this by dyadic dilations. And therefore, we will just seek conditions on this set E for the LP boundedness of our maximal operator. So there are 2 maximal operators. There is the global one, which is the interesting one for the pointwise convergence problem. So we take the soup over all T in E, and then also the scaled variance. This is the set gamma of E, 2 to the minus ks, where s is in E and k is an arbitrary integer. And then there's also the local variant of it, where we just take the soup over the dilations in E, which is sort of a really important tool. Understanding this local variant is an important tool for understanding the global variant. And for the problems that we discuss later, in some sense, like if we ask about boundedness of a maximal operator from LP to LQ, the global variant that I've written here actually doesn't make any sense because the scaling is wrong. And so we're kind of more interested than in the local variant to start with, but I'll discuss that later. So depending on assumptions of E, this we're interested in these operators. Okay, so let's see, can you see the screen? Yeah. So the conditions on E that are relevant for our theorem are formulated in terms of the dimension of E, but there are lots of dimensions and one has to pick the right one. So it's not the Hausdorff dimension, it is the Minkowski dimension. And the Minkowski dimension is the dimension which is related to quantifications of compactness or pre-compactness, right? So we're trying to cover the set with intervals in our case of the set E between 1 and 2 with intervals of length delta. We're gonna take the minimal number that's needed to cover the set. And then we look at the behavior of this covering number. So if this covering number could be bounded by, it's always bounded by 1 over delta, but it could be anywhere between 1 and 1 over delta. And so we define the upper Minkowski dimension as the smallest number beta, such that n of E delta is dominated by 1 over delta to the beta, maybe up to an epsilon. Okay, so this estimate with a constant depending on epsilon here, the red estimate is true for all epsilon, and so beta is defined as the upper Minkowski dimension. Just as an example, if we take the Cantor middle third set, for that example, the Hausdorff and the Minkowski dimension are the same. They're both log 2 for base 3. We could also take the example that I mentioned before, namely the sequence of 1 plus 1 over n to the a. Then the Minkowski dimension, the Hausdorff dimension is clearly 0. This is irrelevant for us, but the Minkowski dimension is 1 over a plus 1. It's in particular for, okay, why doesn't this work? Something is bad here. Okay, good. We get the following result. Given our set E, we compute this index beta, the upper Minkowski dimension, and we let P of E equal to 1 plus beta over D minus 1. You see this varies between 1 and the Stein exponent D over D minus 1. And then it turns out that the local and the global maximal function that I've written are bounded on LP for P greater than P of E and unbounded for P less than P of E. So we cannot quite settle the endpoint, and we do not expect to settle the endpoint with our notion, which is somehow epsilon imprecise, right? So more finer conditions would have to be written to look at the endpoint. Okay, so there is a related statement for pointwise convergence. We have pointwise convergence for P greater than this critical index, and by this very important famous theorem by Stein that I mentioned before, one can show, it follows that if P is less than P of E, there is a function such that the averages diverge for almost every X. So pointwise convergence is really linked to the maximal function. Okay, so I wasn't going to do many proofs, but there is sort of a very basic idea which one can understand, with very basic knowledge of Fourier analysis, and I would like to describe this. So this argument will settle the problem for the local maximal operator away from the endpoint. And then to do more, understand what happens at the endpoint, the questions become increasingly technical. And so perhaps this is not quite suitable for a talk, but let me explain the basic idea. So the basic idea is regularization of the measure. So how do we do this? We look at the Fourier transform and we just gather the contribution from large frequencies which are comparable to 2 to the j. So we make a smooth cutoff. Sometimes we call this a little bit Paley cutoff of that measure. And a very important observation is that the Fourier transform of sigma decays at infinity, and it decays like the C parameter to the power minus d minus 1 over 2, so that p's corresponding to frequencies of size 2 to the j decays like 2 to the minus j d minus 1 over 2, which gives you a favorable L2 estimate. But we're not interested in the L2 estimate for the measure itself. We're interested in the maximal function. And so what we're going to do for each of these pieces, we're going to form the maximal function. So we replace sigma by sigma j. We form the maximal function. And then we like to derive a quantitative estimate for the maximal function for the jth piece. And I'm talking on this slide just for the local maximal function. So the t varies on the set E between 1 and 2. So if we have that quantification, then we just sum over j and see what we can get with it. Right? And so the basic estimate is written here in blue. The maximal function for the set E of the jth piece has a bound which involves a decay 2 to the minus j times d minus 1 of the conjugate exponent p, and another factor which involves the covering number which appeared in the definition of the Minkowski dimension, n to the power 1 over p. So that's the constant for the jth piece. All right, let's stare at this estimate a little bit and let's see what we would do. So there's the realization that if you localize the operator on the Fourier transform at frequencies 2 to the j, then the kernel that you get doesn't essentially much over a set of diameter 2 to the minus j. And likewise, if you consider this AJTF as a function of t, if you wiggle t over a set of diameter 2 to the minus j, it also doesn't change much. So heuristically, we can ignore at what happens in these intervals. And so we can replace the set E by the endpoints of the optimal covering lemma. So we cover the set E by intervals of length 2 to the minus j, and then we just pretend that the set E consists of the endpoint of those covering intervals. Okay, and we know how many we have n. So what happens for p equal to 1? Well, for p equal to 1, we just say, okay, we just sum over the estimates for all of these endpoints, and we get a bound which is like n. And the p prime is infinity. So this is just the bound that's written here for p equal to 1. We just sum over the estimates for the endpoint. And for p equal to 2, we can do a little bit better. Rather than summing, because we have an L2 norm, it's advisable to replace the soup over the endpoint, not by a sum, by the sum of squares, so a little L2 norm. And so we get this n to the power 1/2, and then we take it out, and then we can apply by Poincaré's theorem the information that is given by the Fourier transform of the measure sigma j, the way sigma j hat decays, and we get this bound to the minus j d minus 1 over 2 there, right? So we look at this estimate, and we have two easy estimates for p equal to 1, one for the other one for p equal to 2. We interpolate, and we get this estimate. All right, and so in the end, okay, so now I'm thinking about the definition of Minkowski dimension. I have a bound of n in terms of the 2 to the j to the power beta, which is the Minkowski dimension up to an epsilon. So I put that in, and I get 2 to the j to a certain power. And I would like to sum in j. And whenever I can sum in j, I'm on the good side of of P. So I get an LP estimate. When I cannot sum in J, I'm out of it. And it turns out when this estimate doesn't work, at least away from the endpoint, we have counterexamples that show that it really doesn't work. Okay, so that's a very basic consideration. All right, so let me actually write out the estimate here that we get. This is just the estimate copied from the previous screen. We get the sum over this constant times the LP norm. We can now think about maybe for the endpoint, so these quantities should work. Can we do better than just summing in J? And we thought, wait, could we do better? Yes, we could. We could actually take the sum of squares, and then we could even take the LP prime norm. But that was still not sharp from the counterexample. So the counterexample suggests that we take the sup in J, and that should really be the necessary and sufficient condition. So you see this conjecture here that for the local maximal operator, the sup over these quantities governs the result. So I should be careful. This is for P strictly between 1 and the Stein exponent. There is a conjecture for D over D minus 1, which is different, which I do not want to discuss here. And so for the global maximal function, one should get a similar statement, except the LP boundedness is replaced by what we call weak type PP property, which is in fact enough for pointwise convergence. All right, so we know lower bounds. We didn't know how to prove this conjecture. So we thought perhaps we should check it on radial functions. And it turns out that the work on radial functions actually confirmed basically all conjectures that we had for various LP to LP estimates in various regimes. So there's another paper where this conjecture is confirmed on radial functions, which of course doesn't give any clue on how we should do general functions. And then later there was this paper with Terry Tao and Jim, where for some sets E, this conjecture is confirmed. For example, for the sequence that we discussed, if the set E is just 1 plus 1 over n or 1 plus 1 over n to the A, then this conjecture actually gives you the sharp bound. So we prove an endpoint result. For the Cantor set, the Cantor middle third set, the endpoint at the critical P of E should be true, but this is still an open problem. So for some of you who are interested in this kind of thing, that's, I believe, quite a challenging problem. It could be that it's false and this is a sort of just an unknown counterexample, but we don't know what happens. All right, so this is sort of the work in the 90s, but I should really move on to what was recently done. So far, we just considered LP to LP estimates. And then for the local maximal function, we would like to improve. So the local part should go from LP to LQ. Now LQ is only more restrictive than LP on a local level. So this is really a local property. And therefore it makes sense to restrict to the dilations between 1 and 2, which we will do for the remainder of the talk. It's also mandated by scaling considerations. You could do a different scaling, which is written here. One could consider a different scaling and then prove theorems for that. But this is possible, but it doesn't really add much of insight to the problem. So we'll just stay with the local part. There are results for LP improving. So if we just take a single average, set E is just one dilation, this goes back to Strickhart's in a remarkably early papers in 1970. And we have standard proofs for Strickhart's estimates now by Littlewood-Paley theory, but Strickhart's didn't have Littlewood-Paley theory to that extent. Those tricks were not known to him in the 1970s. This was even before the Hardy space paper by Pfefferman and Stein. And so this is quite remarkable that you could prove the endpoint at the time. He proved an endpoint, that's the point. And then for the full maximal operator, this goes back to the thesis of Schlag, which is a very important paper, and then a follow-up paper by Schlag and Sog. Later, Sang-Hyuk Lee provided certain endpoints for this result. And I will show a picture later to discuss what the results are. So just for 2 minutes, maybe, so you might think, why are we really interested in the LP improving properties for these maximal operators? I mean, it probably doesn't add anything for pointwise convergence, and to the best of my knowledge, it doesn't. It turns out that the estimates that Schlag got were extremely interesting, and so just new phenomena that were shown up, but still that doesn't motivate an application. But there is a recent motivation from the theory of weighted norm inequalities. So this goes via a technique which is pioneered by André Lerner about a sparse bound. So let me just digress for this for a moment. So our motivation is by a paper by Michael Lacey, who proved sparse bounds for spherical maximal operators in LPQ, improving bounds due to Schlag, and Strickhardt played a role in this proof. Okay, so there's a long history, or it's well, a really large series of papers, and it would take me quite a while to discuss papers in that subject. So I will refrain from this, but just give you a basic definition. A sparseness is about the collection of dyadic cubes. You imagine a grid, you cover the Rn by cubes of radius 1. There are lots of cubes, they're all disjoint. But then you can also cover by a grid of cubes of, well, side length, I should say, not radius, side length 1/2 or 1/2 to the n. For every scale, you get a grid, and all of these are the dyadic cubes. You put them all in a family. They're highly non-disjoint, they're highly overlapping. And so we're trying to find the notion of a sparse collection which isn't quite as overlapping. So any disjoint of a collection of such dyadic cubes would have to be considered sparse, but sparse is more general. We will allow some covering, infinite covering. So we say collection is sparse if for every cube in this collection, there is a subset of the cube which makes up most of the cube, so more than half of the cube. And these subsets, E sub q, they are pairwise disjoint. So that is a sparse collection. And then we have for a pair of functions, a given function f and perhaps a weight omega, well, don't have to consider it as a weight. We consider basically, I would say, a sub-bilinear form where we do the following thing. Given two exponents P1 and P2, we sum over the measure of the cube times the P1 average of f. So we take f to the power P1 and average that, and then take the 1/P1th root times the P2 average of omega. And you should somehow think if you have LP boundedness, then it's pretty easy to prove such estimates for P2 being the dual of P1. But if you can go lower than the dual of P2, then you have a non-trivial estimate. Right? And so for us, our operator, now this is really for the global operator. For the global operator, with the original rescaling, we try to pair the global operator with the weight, and then we would like to estimate this by a sparse bound of the above form, where the sparse bound may depend on the function and may depend on omega. And so the right estimate is to take the sup over all sparse bounds and to ask for an estimate like that. Okay, and then we say that the operator is in the sparse domination class relative to the exponents P1 and P2. All right, so this was, as I said, the LP improving properties play already a big role in various papers, quite a number of papers, but this connection was highlighted in recent joint work with David Beltran and Joris Roos that I mentioned before, where there is some direct relation of the sparse bound for the global operator and the LP improving estimates for the local operator. And so I give you the connection. I have two sets. Given my set E, I look at the maximal function that we're interested in, the global one. I assume for an exponent P that we have a weak type estimate and also a dual strong type, restricted strong type estimates. If you don't know what that means, just think of PP and QQ estimates. And then more importantly, the third one is the LP improving estimates for the local operator. Suppose we have that. That gives us a certain exponent sets of P's and Q's. And then there's a sparse exponent sets for which the sparse bound that I mentioned before is valid. Typically 1 over P2 is greater than 1 over P1 is interesting here. All right, and so if we now, the theorem is up to endpoints, we have two diagrams. We have the exponent set on the left-hand side, and we have the sparse set on the right-hand side. And you see that there's a correspondence. If 1 over P, 1 over Q is in the region on the left-hand side, for which we have a good estimate, then 1 over P, 1 over Q prime is in the region of the right-hand side. There is a slight additional assumption, which is some regularity assumption that I've suppressed here, but it has to say that. And it's also, this correspondence is only for the interior of the set. So this is up to the boundary. It's a little bit better than what I say, but say essentially it's up to the boundary. But at least this gives you some indication that LP improving for the local operator is relevant for certain behavior of the global operator, namely in terms of these sparse bounds. Okay, so now I'm getting behind in time here. So what we are interested in drawing the set of 1 over P, 1 over Q for which the local maximal operator is bounded. And we ask two questions. What is the type set? If we are not interested in the type set up to endpoints, we're just asking what the closure is of the type set. And the other question that we ask, well, typically these type sets are always triangles, quadrangles, or polygons. Which sets can actually arise here? And so there is a recent, fairly surprising answer actually in this paper with Joris. And in order to formulate a result, what we have to do is we have to sharpen our notion of Minkowski dimension. We originally thought the Minkowski dimension was just it. We found that certain operators which equal Minkowski dimension behave totally different. So it turned out that there is another type of dimension, the Aswad dimension. And so what is this? This is some kind of a local Minkowski dimension, the largest local Minkowski dimension. And so what we're doing here, we take a fixed interval of lengths greater than delta, and then we're just focusing on that interval. And we look at the covering number for that interval, and we do not want to bound it by delta to the minus power, but delta divided by the reference length of the reference interval to the power minus gamma. So that's a potentially larger number than the Minkowski dimension, and the smallest gamma that we can, for which we have this estimate, we call the upper Aswad dimension. We call it the Aswad dimension. All right. Now for the Cantor set, Minkowski and Aswad are the same. For the other basic example that we discussed, namely just the sequences 1 over plus 1 over n or n to the a, the Minkowski dimension depended on a, but the Aswad dimension is actually 1, which indicates that if we move to the left endpoint to 1, the set is far more crowded elsewhere, which of course is intuitively clear. Right? So the Aswad dimension is larger. So the result, there is a result which depends on 4 endpoints, 4 points in this 1 over P, 1 over Q planes. You do not have to understand what these are. So I should rather discuss this result in a picture. This result is sometimes sharp, sometimes not. In the model cases that I mentioned, it is sharp. Okay, so, and then we say, so there's a certain quadrangle, and 1 over P, 1 over Q is in this quadrangle, and we have a result. And I really wonder, so this is now where I really needed my iPad. I guess I wanted to draw in this picture a little bit, but I kind of have to talk you through it. Okay, so we have this quadrangle, we have these points. Q1 is just a point for infinity boundness, Q2 is the point for LP boundedness. Q3 is the point for LP to the dual LP prime boundedness, and Q4 is perhaps the interesting point. And so for the result, that's just for one average. That was the old Strickert's result. We have beta, the Minkowski dimension, of course, is 0, just 1 point. Gamma is equal to 0. And this point Q3 of beta, you see that two intersecting dotted lines. And the Q3 beta moves down to the intersection of these dotted 3 lines. And the Q2 beta on the diagonal moves up to 1, 1. And what you get then is a triangle. And so Strickert's proved the LPQ estimate in that process, except for beta equal to gamma equal to 1, the line connecting Q2 and Q3 becomes vertical. Okay, that's just what it is. All right, now what happens if we fix the Minkowski dimension and we change the Aswad dimension? So then the Q4 slides on this line, which happens to have slope 1 over d, up and down. So if gamma is smaller, it slides up and the blue region gets larger. If Q4 gamma goes to 1, it slides down to a certain Q4 of 1. All right. And so for the Cantor set, we have the better result. For the sequence, we have the worst result. Then there's also a result for radial function. And you see that where the point R of beta is indicated there. We just get the triangle Q1 of R of beta Q2 for radial functions. And this indicates that all counterexamples for this type of LP improving estimates, well, the interesting counterexamples, let's say not all, but the interesting ones are actually non-radial. Okay, so there's perhaps more to say, but so then our new theorem is if beta is the Minkowski dimension and gamma is the Aswad dimension, we have boundedness in this region for arbitrary beta and gamma. We actually replace this dimension by a slightly better notion of quasi-Aswad dimension, but I will, if I have time, I will discuss this a little later. I should also say that the case d greater than 3 is always more easier than the case d equal to 2. And this even came up in the thesis of Schlag, who did the d equal to 2 thing for the global maximal operator. And so we can explain this in this region here. So I cannot really draw this, but so in d greater than or equal to 3, the point Q4 of gamma moves up. It's actually on the right of the line p equal to 1/2. And what happens then is that you can interpolate an L1 and infinity estimate with a Strickert's type LP to L2 estimate and work with L2 in that argument. That makes the argument easier. If the point Q4 is on the left of this line p equal to 2, then we cannot do this and the argument get harder. So there's a distinction between difficulty between these theorems, between these two papers. Okay, so I said this result was sometimes sharp and sometimes not. And it turns out in the end to rather, it's not clear when exactly it is sharp. Well, it's clear when it is sharp, but we do not have a sharp result for all sets. So we can ask an easier question. And the easier question is, well, what could the typeset look like? Does it have to look like a quadrangle like this, or could it look like in a different way? Right? And so what we actually get is from our theorem that I just stated, this quadrilateral that was drawn is always contained in the closure of the typeset. That's a sufficient condition. There's also a necessary condition. If we draw the quadrilateral where gamma is equal to beta, this gives us basically the same figure, but a larger quadrilateral, then we get a necessary condition. And so that means the typeset has to be between these two quadrilateral. What can it be there? And so the somewhat surprising answer is that it could be essentially everything which is not ruled out by trivialities. Okay, so for any closed set in the unit square, the following are equivalent. There exists a set of dilations such that the closure of the type set is that set. That's equivalent with saying the set has to be convex and lies between Q beta beta and Q beta gamma. Let's look at the picture here. Let's see what that means. So the blue region is the one for which we can always prove a theorem. The blue union the red region is the region where we have a necessary condition. And then what we're saying, any convex set which is between those, and one of those convex sets is drawn on the right-hand side, any one of those is the type set, is the set of LP LQ boundedness up to endpoints, is the closure of the type set for a particular set E. So we would have to construct a set E for this to be true. Okay, so that's sort of surprising, that and it indicates that the problem of LP LQ improving is far more complicated than the original result in the 90s that we considered just for LP boundedness. All right, and now there is a natural question which I discussed. When is this result that we have for this quadrilateral Q beta gamma, when is it actually sharp? And it turns out, in order to answer this, we have to introduce yet another type of dimension, namely a spectrum of dimension, which, well, we formulated a condition when it is sharp, and then we realized that this condition could be interpreted in terms of a connection which also already was in the literature. And so this is the upper Aswad spectrum, originally considered by Jonathan Fraser at HANU for Aswad spectrum, and then the modified notion that is more appropriate for us was in a paper by Fraser, the two Harris, Troscheid, and Yu. Okay, so let's see what this Aswad spectrum is. There's a parameter theta which varies between 0 and 1. And so we write out exactly the same condition as in the definition of the Aswad dimension, except we put in a restriction for the reference interval. We do not consider all intervals greater than delta. We just consider as reference intervals the intervals of length greater than delta to the theta. For the Minkowski dimension, this reference interval would be just one interval, the underlying interval from 1 to 2. And for the Aswad dimension, we get arbitrarily small reference intervals. So here there's a restriction. Okay, and so this notion of we get then the minimal number of alpha for which this inequality is true. That is the dimension depending on theta, the Aswad spectrum theta dimension. And this dimension as a function of theta is continuous and monotone. When theta is equal to 0, we get back the Minkowski dimension. When theta is equal to 1, we get the Aswad dimension. And it could be everything in between. Since it's continuous, it's not necessarily continuous at the endpoint. So the limit as theta goes to 1 exists, but doesn't have to be equal to the Aswad dimension. It could be strictly smaller. And so that's called the that limit is called the quasi-Aswad dimension. And it's really the dimension that should be used in our theorem. All right, so for examples for the Cantor set, all the dimensions are the same. For the sequences that we discussed a lot, what happens is we start out with, at theta equal to 0, we start out with our 1 over 1 plus a, and then the notion of dimension increases with theta, and at some point it reaches 1. It reaches 1 at a over 1 plus a, and then of course it has to stay the same. It gets larger. And so there's a realization, and I don't have the time to explain this, but this exponent a over 1 plus a happens to be 1 minus Minkowski dimension over a Swart dimension. And one can show this is the earliest time as a function of theta for which the Swart dimension can be reached. In this particular case, gamma is equal to 1. Okay, another example, and so this notion will play a role in our sharpness theorem. So there's another example, 1 plus this sort of the sparse 2 to the minus squared of n, where the Swart spectrum is identically 0, also therefore the quasi-Swart dimension, but the Swart dimension is actually 1. All right, and so that's where the two Swart dimension and Minkowski and quasi-Swart dimension differ. All right, so now for sharpness, we look at this Swart spectrum that we just discussed, and we say that a set is regular with respect to the parameters of Minkowski and quasi-Swart dimension if, as a function of theta, the spectrum dimension, depending on theta, reaches gamma exactly at 1 minus beta over gamma. So for theta between 1 minus beta over gamma and 1, it is equal to the gamma, the quasi-Swart dimension, which in many cases is the Swart dimension, but not always. All right, and it turns out it can never reach that before 1 minus beta over gamma. And so this condition is true for the Cantor set trivially. It's also true for our sequences. It's true for lots of other examples that we computed. But in those examples, whenever this happens, our theorem is sharp, right? We call this quasi-Swart regular, whatever. Whenever we have this regularity theorem, then it's sharp. But in many cases, the set is not quasi-Swart regular. Okay, amazingly, I'm basically in time, so I'm coming to my last slide. So there's a theorem here, which essentially is a trivial observation, but it sort of changed our point of view totally about this problem. So we thought at the time, maybe we had this sharp result for all sets. We don't at all. So what we're doing here, so we're taking these quasi-Swart regular sets for which we have a sharp theorem, right? And now we take a set which is a finite disjoint union, could be even just finite union of quasi-Swart regular sets with different parameters beta, gamma, I. And then it's very easy to realize, to prove that the type set, the closure of the type set is simply the intersection of the quadrilaterals related to each of the quasi-Swart regular sets. And of course, the intersection of these quadrilaterals for different values of beta and gamma doesn't have to be a quadrilateral. It could be an arbitrary polygon. It could be a very complicated set. So that polygon should still be between Q beta beta and Q beta gamma, where gamma is the Swart dimension, but it could be a general polygon. And so in that picture that I drew, we could take every set, we can take lots of polygons. And so then we think, I mean, could we perhaps get some typesets which do not look like a polygon, which look like a curved set? And indeed, that could be true. So this would be true if this theorem that I stated here was true for countable unions. Unfortunately, it's not for countable unions. And if one thinks about it, it's totally absurd. For example, you could take for the set E to be the rational numbers, you get the best result. And for the constituent sets, you take just a set of 1 point, right? The set of rational numbers is a countable union of 1 point sets. And the intersection of the 1 point sets are big. So we get good result for each 1 point set. The intersection is still good. And for the rational numbers, we get basically only Stein's result. So that's absurd. But nevertheless, the idea in this theorem can be taken over to suitable, very carefully selected unions, countable unions of set E. And so we draw an arbitrary set and we try to realize the set as a countable intersection of enveloping quadrilaterals. And then we can get the theorem as indicated in the proof. So this idea at least works. Now, a big open question is now, what is the right characterization for an arbitrary E? You give me E, and I would like to see what is the typeset. Is it perhaps possible to decompose the set as a suitable countable union of quasi-Assad regular set, and we could have a condition like that, but that seems very complicated and very difficult. So we do not know what the answer is to that question. And I guess with this, I'm at the end of my talk, and I really would like to thank you for listening and coming.
Okay, thanks a lot. So are there any questions? Okay, in your
what if you take ellipses rather than spheres? Has this problem been studied much? I think there are some results.
Well, where if you take ellipses and you just do this type of result, then you get the same. And the interesting result for ellipses are those where you have, where you vary not just the dilation, but you vary the two axes. So you get a 2-parameter dilation set. And so, I mean, there's some standard results, but for the good results, that's actually, that can be quite difficult. So what this setup will work with is if you sort of, and there's this notion of cinematic curvature, which comes up for the wave equation. And if you can observe that structure, I think the results will work. And this is related to this point Q4. But it will not, for example, the results for an arbitrary surface would be probably quite different for LPLQ. But so just dilating one ellipse is like dilating one circle. Yeah. Any other questions?
Yeah, just continuing with Professor Wenger's question. So can't one take the conversions on the diagonal, because you said you have 2-parameter on the ellipse, right? So,
right. That's a very good question. So you take, a question which I didn't touch on at all in the talk, but so you could take the ellipse with axes A and B, right? And then you can take just for the local maximal function, maybe you can soup over A and B, and you can ask what is the precise range of convergence. You can do this for any dilation set. You can do it for the full dilation set. I believe this is not, you get certainly good results in higher dimensions. I'm not exactly sure. I don't think anything is proof for the circle for this. Because you just, so if you take the latest local smoothing result by Guth, Wang, and Zhang, and you would apply that, so you basically gain 2 over P derivatives, you're just out of the range for this maximal function. You wouldn't be able to prove that. And so I don't know what the answer is. I think it should still, perhaps there should still be a bounded range for the circle. In higher dimensions, I would expect whenever the critical P that you get is less than 2, then you should get the sharp result and probably be able to prove that it's sharp. But in low dimensions, it's a big problem. And there are a number of papers which have addressed this problem.
Okay.
In higher dimensions.
Okay, could you please also send a reference later? That would be nice.
A reprint? I'm sure
a reference, yes.
You mean the slides or a reprint?
No, sorry. Of course, the slides, and you said there are a couple of results in that direction. So some sort of reference.
I would have to, yes, I would have to look them up. So I know there's, yeah, so I think sort of the really difficult results that pertain to ranges for p greater than 2, where the L2 result fails. That's usually the harder one. There are some results by Burak Erdogan. There's also the problem where you take the soup over all ellipses. So in other words, for the circle, this doesn't make sense. You can rotate, the circle stays the same, right? But for the ellipse, it doesn't. So you take you do not fix the direction of the axis, but you could take arbitrary ellipses. And so I'm not exactly sure whether he addressed that one or just the fixed axis problem. But and so I know that he didn't prove boundedness of the operator, but he proved preliminary estimates. So what exactly does the norm, like independence of the frequency localization, look like? What are Sobolev bounds, perhaps, things like that.
Okay.
See, there would also be a problem.
I can send it to you, yeah, sure.
Okay, thank you.
There could be a problem where you have something like an ellipse, but at some point, the Gaussian curvature becomes 0, or the curvature becomes 0 at some rate, and then.
Right. And this will probably be very, so that's what I was indicating before, that the first question you can ask for any convex body, and it should be interesting. And so I think for the LP boundedness, we would be able to prove pretty satisfactory theorems using our own results, Steve. I mean, with new techniques.
I think there's something.
Yeah.
I think I saw a paper once that dealt with that, but I can't remember.
Well, there are lots of papers which deal with the problem for the full maximal function. But so if you do LP, LQ improving, there is this, as I mentioned, this notion of, so-called cinematic curvature, which is not just related to the curvature of the body, but it's also related. So the cinematic curvature, the failure of that is a more serious problem. So I wouldn't know what the sharp results should be. It's probably quite a complex problem and possibly a very interesting problem. Yeah.
Another question. In one of your chapters written with Rogers and Shangukli, so there you mentioned that how the square function for this, this family of operators and the square function for the Bochneries, they are sort of equivalent, right, up to some parameters. And then, one would like to say that what can one say about the Bochneries means the convergence for these on fractal sets? Like, is there some correspondence here?
That's a very good, and we're actually thinking about that. That's a very good question. I mean, so this square function that you mentioned, and the idea goes back to an old paper by Kaneko and Sunucci.
Yeah.
So this idea actually relates to this other paper that I mentioned on, which I didn't have a chance to talk about here, about variational estimate. So where instead of the soup in T, you seek to understand variation norm estimates. And then this relation with the square function result is very important. But so whether you can do this for fractals, I'm quite intrigued by that question actually, but I can't give you a good answer right now.
Yeah, okay. Perhaps one has to take, you have to use Frosterman's lemma to get that measure, and I don't know.
Yeah, so see the problem with Frosterman's lemma is very much tied to the Hausdorff dimension.
Yeah.
The Hausdorff dimension plays absolutely no role, except of course in those examples where all the dimensions are equal. So in the self-similar case, I think you could. This could be a very good idea for the self-similar sets to work with those notions. I think so, yeah.
Yeah.
I think in some talk, Jos Savage pointed this out to me, that some of the theorems in this particular case where Hausdorff dimension is equal to everything else, the proofs have a sort of an easier approach, it's or different approach. Yeah.
Okay. So are there any more questions?